Section 6.3, losses as a function of load. We're gonna look at the losses in an electrical machine, and we're going to reference those losses in terms of the load that's connected to this electrical machine. That's important for a lot of different reasons. But the first thing I want you to think about is this, okay? When we talk about the power, the nameplate rating of an electrical machine, that is the power available at the shaft to do work, okay? Now, so an electric machine, let's say a motor, running at no load, by definition, does not produce any useful power, okay? It's only when a load is connected to this machine that at that point we can say that the machine is producing useful power available to do something, to do some work. Now, let's look at this in terms of, let's look at a graphical representation of this idea. Okay, so if we think about a motor and it's not, it has no load, it still needs some power to be able to turn, to rotate. Okay, so we must have some power from the line for the motor just to operate. Again, though, that power is not, what we're thinking about in terms of useful power. This no load power has to overcome the losses that are associated with the power. This includes the friction, the windage, the iron losses, and at no load, the copper losses in the shunt field, okay? So we're talking about, these areas. This is what an unloaded motor must overcome just to be able to turn. So it must draw that power from the line to be able to do that. Now, there are also I-squared losses in the series, armature, and commutating portions of the motor, but those are very small, seldom more than 5% of the full load current. So we usually don't consider those. There's no real significant current flowing in the armature, right, until we connect a load to it. So as we load this machine, the current increases in the armature circuit. And then the I-squared R losses in return will also increase as the current begins to increase in the armature circuit, okay? And then all other windings that are in series with it. On the other hand, the no load losses, these guys, they're not really going to change, are they? They're going to remain the same regardless of whether the machine is loaded or not. They're constant. One thing that might change is, significant heating or temperature increase, and maybe some of those things increase from there. But really, the no load losses, would be constant, but the total losses, because of this current flowing in the armature, increase with load. And these increases are converted to heat, and the temperature of the machine rises as the load increases. However, there's, and you would think initially, say, well, I can just limitless current I can draw. But there is a threshold that can't be violated, and that has to do with the insulation that is associated with the electrical machine, primarily the insulation and the conductors. And there's a limit to the power based on the insulation class that the machine can deliver. This temperature limited power enables us to establish something called nominal, and if you want to think about nominal, think about name, right? And if you want to think about name in a motor, think about nameplate, okay? It's the rated or nominal power. And that is based on the insulation class that the motor has. A machine that's loaded beyond its nominal rating will usually overheat, and the insulation will deteriorate more rapidly, and eventually you will shorten the service life of the machine. It happens every day. It's a leading cause of motor failure. If a machine runs intermittently, it can carry the particular overloads without overheating if the operating time is short. So, maybe a 10 kilowatt motor can readily carry a load of, say, he gives just a number, 12 kilowatts, as long as it's for a very short period of time. For higher loads, the capacity is limited by other factors, usually electrical, okay? But, in a particular instance, a motor rated at 10 kilowatts can operate in excess of that for short periods of time. So he goes on to say it's physically impossible, say, for a 10 kilowatt motor to deliver 100 kilowatts, even for a millisecond, just because it physically doesn't have the capacity for that. Okay, so take away from this that the losses are a function of the load, that there are these losses, no load losses, and they're constant. They're basically the same regardless of the load or not. But when current starts to flow through the series armature and commutator, commutating poles, then I squared R losses increase, and that is where the overall total losses increase in a loaded motor over a non-loaded motor.